Okay, so let's move on to the ROC curve, and also we're going to talk about something else related called the AUC curve.
Wait till you see the ROC and the AUC. They're cool, yeah, StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about ROC and AUC, and they're going to be clearly explained. Note, this StatQuest builds on the confusion matrix and sensitivity and specificity StatQuests. So if you're not already down with those, check out the quests. Also, the example I give in this StatQuest is based on logistic regression. So, even though ROC and AUC apply to more than just logistic regression, make sure you understand those basics.
Okay, now the reason he's going to use logistic regression is because, as we just saw in logistic regression, we can move the cutoff point to various places. So we could have a cutoff point at 80% or 50% or 20% or whatever we want. We can adjust the cutoff point, right? We said that, and that's going to be key to what we're doing next. So you have to remember that the cutoff point is adjustable.
Let's start with some data. The y-axis has two categories.
Okay, now this is a little, I like to complain about this graph. First of all, we have not obese and obese, and somehow it seems like that it seems trivial, but it just seems natural to put this as red and this is blue, but he chose the opposite, right? So I would have put red up here. Second of all, there's sort of redundant information here because he shows that the non-obese have to be down here and the obese have to be up here, but he also uses color to distinguish them. So in a sense, it's not really, you don't need color because if a dot is down here, it means it's not obese. And if a dot is up here, it means it is obese. So you don't really need the color. So the color is sort of redundant information, but it's okay to have it, but it's kind of odd to have redundant information in a graph, and it is redundant in this graph. So just be aware that that's the case. Okay, and also we just have to remember, because it's not natural for me to think of blue as being the obese and the red as not being obese. But anyway, we'll leave it, let it go like that.
Obese and not obese. The blue dots represent obese mice, and the red dots represent mice that are not obese. Along the x-axis, we have weight. This mouse is not obese.
So just to reiterate, so any dot that's down here represents a non-obese mouse, and any dot that's up here represents an obese mouse. And of course, there are only two possible heights because this is categorical variable, and there's only two values for it. So it can either be not obese or obese. And then we also have the coloring, which says, so in other words, you could never have a blue dot down here because that would be, the blue dot means it's not obese, so you couldn't have it down here. You could never have a red dot up here because the red dot means not obese, and this would mean that it was obese, so that doesn't make sense.
Obese and not obese. The blue dots represent obese mice, and the red dots represent mice that are not obese. Along the x-axis, we have weight. This mouse is not obese, even though it weighs a lot. It must be Mighty Mouse and just full of muscles. This mouse doesn't weigh that much, but it is still considered obese for its size. Now let's fit a logistic regression curve to the data. When we're doing logistic regression, the y-axis is converted to the probability that a mouse is obese.
Okay, so remember that. First of all, we talked about in the last section, we talked about which we had a criteria for choosing among all the different logistic curves, one particular one. So now we have one particular logistic curve. So this is supposedly the best curve, or anyway, this is the logistic curve we're going to use. And then he says that the logistic curve, because it goes between 0 and 1, he says converts the weight into, what did he say actually? Let's see. Sorry.
Size. Now let's fit a logistic regression curve to the data. When we're doing logistic regression, the y-axis is converted to the probability that a mouse is obese.
Okay, so the y-axis is converted by this curve, so to speak, to the probability.
Now let's just look at the curve. If someone told us that they had a heavy mouse that weighs this much,
okay, so now we have the curve, which is our model, and it allows us to make predictions. So we can say, suppose a weight was out here, and we could ask, what does our model predict? That is, we have a classification model basically, and it's going to predict either obese, which is up here, or non-obese, which is down here, right? And so for this particular weight, if someone had this weight or some mouse had this weight, then it's going to predict up here, very high probability of being obese. In other words, it's probably going to predict that it's obese. But anyway, this is our model, right? Just like we have J48 to do modeling for us, just like, we train a model in J48 and then we have a model to make predictions. We have a neural network, we train it and it can make predictions. We have, whatever other models we've talked about. This is now our model, this curve. So the curve could have been over here. It could have been over here. It's always going to have this shape, but it could have been shifted to the right or the left. So we could have had different, and that would mean different models. But right now we have this model. So this dot will get predicted as obese.
then the curve would tell us that there is a high probability that the mouse is obese. If someone told us that they had a light mouse that weighs this much, then the curve would tell us that there is a low probability that the mouse is obese. So this logistic regression tells us the probability that a mouse is obese based on its weight. However, if we want to classify the mice as obese or not obese, then we need a way to turn probabilities into classifications.
So how are we going to do that? How are we going to turn probabilities into classifications? We said that we're going to use a threshold. So maybe the most natural threshold is 0.5, but it's not, we could change it. In fact, that's what we're going to be talking about, changing it. But anyway, the most natural one is perhaps 0.5, but it's not necessary to choose 0.5.
One way to classify mice is to set a threshold at 0.5 and classify all mice with a probability of being obese greater than 0.5 as obese.
So anything that's, because if we use 0.5 and we have this curve, then we go 0.5, we go to here. Anything that's to the right of this weight is going to be up here, and so it's going to be classified as obese, anything to the right of this weight here.
And classify all mice with a probability of being obese less than or equal to 0.5 as not obese. Using 0.5 as the cutoff, we would call this mouse obese, and this mouse not obese. If another mouse weighed this much, then we would classify it as obese. And if another mouse weighed this much, then we would classify it as not obese. To evaluate the effectiveness of this logistic regression with the classification threshold set to 0.5, we can test it with mice that we know are obese and not obese.
So we can, we have a test set, and we're going to see what the model makes, what predictions it makes. So like here is our test set. Now he's using all this as red, which, okay, so these mice are all not obese. So he's putting the dots as red. Okay, so these dots are not obese. Now we can see how our model does with these. So if you put it, if this mouse is red, it means it's obese, but its weight is here, then I go up here and it's definitely going to classify it as not obese. This one is definitely going to classify it as not obese. But this one, we go up to here, okay, it's still not obese. And this one, though, we go up to here in our model, and it's definitely going to classify it as obese, but it's not obese. We have red as not obese.
Here are the weights of 4 new mice that we know are not obese.
That's our test set.
And here are the weights of 4 new mice that we know are
And
obese.
that's our test set too.
We know that this mouse is not obese. And the logistic regression, with the classification threshold set to 0.5, correctly classifies it as not obese. This mouse is also correctly classified. But this mouse is incorrectly classified. We know that it is obese, but it is classified as not obese. The next mouse is correctly classified. But this mouse is incorrectly classified.
Okay, this one is red, so it's not obese, but it's heavy. So in our model, the model will predict that it is obese. So that's an error. And this one is blue, so we know that it is obese, but its weight is low. So our model is going to predict it here, so it's below the threshold, so it's going to say it's not obese, even though it actually is obese because it's blue. Our model will be making a mistake for this as well.
The last 3 mice are correctly classified. Now we create a confusion matrix to summarize the classifications. These 3 samples were correctly classified as obese, and this sample was predicted to be obese, but was not obese.
So this one was predicted to be obese, but it's actually red, which is not obese. So where do we put that here? It's actually not obese, but it was predicted to be obese. So there's one like that.
These 3 samples were correctly classified as not obese.
So these 3 were correctly classified as not obese, right? Because they are red means they're not obese. And the model, when we put it into the model, we get not obese, not obese, not obese. So these 3 are correctly classified as not obese. So they're predicted as not obese, and they actually are not obese. So there's 3 right there.
And this sample was predicted to be not obese.
So this one was predicted to be not obese, but it's blue, so it is obese. So it's wrong. So that's here. It was predicted to be not obese because it's not very heavy. So it's predicted to be not obese, but it actually is obese. So it's predicted to be not, but it is obese.
Even though it was obese. Once the confusion matrix is filled in, we can calculate sensitivity and specificity to evaluate this logistic regression when 0.5 is the threshold for obesity. Little bam, because so far, this is all review. Now let's talk about what happens when we use a different threshold for deciding if a sample is obese or not.
So before we listen to him, let's just think about it. So what happens if we set the threshold way up here? What happens if we set it way down here? So if we set it, for example, way down here, then first of all, we know that it's going to say that almost everything, it's going to classify almost everything as obese, because if it's way down here, everything above here is going to be classified as obese. So that means basically everything is going to be classified as obese. Anything that gets mapped to anything higher than here is going to be obese. If we set the threshold up here, so like 0.9, we set it up here, then virtually nothing is going to be classified as obese, and virtually everything is going to be classified as not obese. So the question is, how is this going to affect our accuracy and our error rates and so on? So if we set the threshold down here, the cutoff down here, then like we said, virtually every instance is going to be classified as obese. So that means we are not going to miss any of the actual obese ones, because like everything is going to be classified as obese. We're never going to, very unlikely that we're going to miss any of the obese ones. So we're not going to miss any of the obese ones. So that means that basically everything up here, we're not going to make any mistakes. So this is from the ones that are actually obese, the mice that are actually obese, we're going to get all of them. We're going to say all of them are obese. So basically this one that was misclassified before is not going to be misclassified because we set the threshold so low. We set it down here so that everything is classified as obese. So this one will also get pushed up to here. So this is going to be 4 and 0. And if you remember what sensitivity means, it's going to take the number here divided by the total number here. If you remember that, or if you don't, anyway, that's what it's going to do. It's going to take this number divided by the total. That's what sensitivity is. It's working in this column, and it's saying take this number divided by the total. Now, right now, this number divided by the total would be 3 out of 4, but if we set the threshold really low, then this one is not going to be misclassified anymore. So it's going to be 4 over 4. So the sensitivity is going to go up to 100%. But we're going to pay a price in terms of specificity, as we'll see. But anyway, just the point that we're doing here is we're thinking about if we lower the threshold, what's going to happen? How are things going to change? We are allowed to lower the threshold, but we want to see what's going to happen when we do that.
Because so far, this is all review. Now let's talk about what happens when we use a different threshold for deciding if a sample is obese or not. For example, if it was super important to correctly classify every obese sample, we could set the threshold to 0.1. This would result in correct classifications for all 4 obese mice.
So you can see, remember that blue means obese, and so this, because this is so low, before this was predicted as not obese, but now since we set the threshold way down here, this one is going to be predicted as obese, and all the others are going to be predicted as obese. So that's why, whereas before there was only 3 that were predicted as obese, now it's going to be all 4 are going to be predicted as obese.
If it was super important to correctly classify every obese sample, we could set the threshold to 0.1. This would result in correct classifications for all 4 obese mice. But it would also increase the number of false positives. The lower threshold.
False positives means that we're going to predict that they're obese when they actually aren't. So when we bring this way down here, we're going to classify virtually everything as obese, including this red one and this red one. These are not obese, and this one wasn't predicted as obese when we had it at a 50% cutoff. This one was. Even this one was a mistake before, but now this one will also be a mistake when we bring this down to here. This one will be predicted as obese or blue when it's actually not obese, it's red. This one was a mistake even at 50%, but this one will now be added to the mistake. So this one was probably 1 before. Let's see that. Yeah, this one was 1 before when we did the 50% cutoff, but now it is 2. Okay.
Classifications for all 4 obese mice. But it would also increase the number of false positives. The lower threshold would also reduce the number of false negatives because all of the obese mice were correctly classified. And it would reduce the number of true negatives because 2 of the mice that were not obese were incorrectly classified as obese. Note, if the idea of using a threshold other than 0.5 is blowing your mind, Imagine that instead of classifying samples as obese or not obese, we were classifying samples as infected with Ebola and not infected with Ebola.
So if it wasn't obese and not obese, but it was Ebola and not Ebola, you know, Ebola is such a dangerous disease, and it's very easy to catch from somebody else. So you can't miss anybody. So then you would want to lower the threshold and say, oh, this person has it, this person has it, this person has it, everybody has it, so we have to quarantine everybody. We can't afford to miss even one person. So we would want to lower the threshold so that we might misclassify people and say, oh, you have Ebola, so you have to be quarantined, but we wouldn't miss any people who actually have Ebola and tell them, no, you don't need to be quarantined.
In this case, it's absolutely essential to correctly classify every sample infected with Ebola in order to minimize the risk of an outbreak. And that means lowering the threshold, even if that results in more false positives. On the other hand, we could set the threshold to 0.9. In this case, we would correctly classify the same number of obese samples as when the threshold was set to 0.5. But we wouldn't have any false positives. And we would correctly classify one more sample that was not obese, and have the same number of false negatives as before. With this data, the higher threshold does a better job classifying samples as obese or not obese. But the threshold could be set to anything between 0 and 1. How do we determine which threshold is the best? For starters, we don't need to test every single option.
So you can see that if you have the threshold here, you just bring it down a little bit more or bring it up just a little bit more, it doesn't really make any difference. You're still going to do the same classification that you would at 50% when you set it at 50%. So some of the shifts that you could make don't make any difference.
For example, these thresholds result in the exact same confusion matrix. But even if we made one confusion matrix for each threshold that mattered, it would result in a confusingly large number of confusion matrices. So, instead of being overwhelmed with confusion matrices, receiver operator characteristic ROC graphs provide a simple way to summarize all of the information.
Okay, so this is the ROC curve that we want to discuss. And the first thing to notice is what are the axes. So you can see that the sensitivity, which is the true positive rate, but the sensitivity is one of the axes. And the other axis is 1 minus the specificity. So it seems like a weird combination of axes, but that's what they're using. So sensitivity and 1 minus specificity, but that's not so weird because 1 minus specificity turns out to be, and you can just look it up on Wikipedia and you can see easily that 1 minus this, or pretty easily, that 1 minus the specificity is the false positive rate. So that, remember, what does that mean? It means, so the false positive rate is here, and it doesn't say it's 1 minus the other, but anyway, the false positive rate is this column. We're working with this column, so the ones that are truly negative. So we're considering of all the ones that are truly negative. So the condition is really negative. From all of those, we want to calculate the number that are false positives. So in other words, the ones that are considered positive, even though they're actually negative. So it's this divided by these two. That's the false positive rate. So that's one of the axes. And the other axis is the sensitivity. So we're going to make, and the thing is that each one of these represents a different threshold. So we're going to move the threshold around like we said, like we were doing. And each time we're going to get different sensitivity we're also going to get a different 1 minus specificity or a different false positive. So we're going to get different dots representing shifting the cutoff to different levels. That's what this ROC curve will be showing us.
The y-axis shows the true positive rate, which is the same thing as sensitivity. The true positive rate is the true positives divided by the sum of the true positives and the false negatives. In this example, the true positives are the samples that were correctly classified as obese, and the false negatives are the obese samples that were incorrectly classified as not obese. The true positive rate tells you what proportion of obese samples were correctly classified.
So in other words, it's this number divided by these two. That's the sensitivity. That's going to be the vertical axis.
The x-axis shows the false positive rate, which is the same thing as 1 minus specificity. The false positive rate is the false positives divided by the sum of the false positives and true negatives. The false positives are the non-obese samples that were incorrectly classified as obese, and the true negatives are the samples correctly classified as not obese.
So this one is going to be this number here divided by these two, the false positives divided by these two, the false positives plus the true negatives.
The false positive rate tells you the proportion of not obese samples that were incorrectly classified and are false positives. To get a better sense of how the ROC works, let's draw one from start to finish using our example data. We'll start by using a threshold that classifies all of the samples as obese. And that gives us this confusion matrix.
So we take a very low threshold, so low that no matter what the weight, we're always going to classify them as obese. So everyone that is obese will be classified as obese. So there will be nobody who's predicted to be not obese from this group. And there will be nobody that is predicted to be not obese in this group. So both this and this will be 0.
First, let's calculate the true positive rate. There are 4 true positives, and there were 0 false negatives. Doing the math gives us 1. The true positive rate, when the threshold is so low that every single sample is classified as obese, is 1. This means that every single obese sample was correctly classified. Now let's calculate the false positive rate. There were 4.
So now we see that these have all become errors. All the people that were not obese are still predicted to be obese. So those are all errors. So we're making a lot of error by doing that. It's in this category of not obese.
4 false positives in the confusion matrix, and there were 0 true negatives. Doing the math gives us 1. The false positive rate, when the threshold is so low that every single sample is classified as obese, is also 1.
So where is this going to be in our graph? Remember that the two axes were, the vertical axis was the sensitivity or the true positive rate, and the other one was the false positive rate was the other axis, or it's also 1 minus the specificity. So this is going to have, on those two axes, so this is going to be 1, 1. So there's going to be a dot of 1, 1 in this curve that we're creating.
This means that every single sample that was not obese was incorrectly classified as obese. Now plot a point at 1, 1. A point at 1, 1 means that even though we correctly classified all of the obese samples, we incorrectly classified all of the samples that were not obese. This green diagonal line shows where the true positive rate equals the false positive rate. Any point on this line means that the proportion of correctly classified obese samples is the same as the proportion of incorrectly classified samples that are not obese. Going back to the logistic regression, let's increase the threshold so that all but the lightest sample are called obese. The new threshold gives us this confusion matrix. We then calculate the true positive rate and the false positive rate.
Okay, so what we're going to do is we're going to raise the threshold to various different places. As we saw, we don't have to do it to every place because some of them don't make any difference. So we're only going to move it to places where it makes a difference. And each time, then we're going to get a different true positive rate and false positive rate, or they could be different. And so we can plot those points each time. So this time, we get to here. We get a point here. And then we're going to do another one. And who knows where it's going to be, but it's going to be somewhere. And we're just going to keep doing that until we've got moved the cutoff bar to all the important places.
And plot a point at 0.75, 1. Since the new point is to the left of the dotted green line, we know that the proportion of correctly classified samples that were obese is greater than the proportion of samples that were incorrectly classified as obese.
Okay, then we can say which cutoff is better, the one that gave us this dot or the one that gave us this dot? And we can answer that question. We can give an answer to that question because false positive rate is obviously something that's not good. So we want that to be smaller. And true positive rate is something that's good, so we don't want that to be lower. But this dot does not lower the true positive rate, right? It's the same as this dot. The height is the same as this dot. But it does lower this, when this is large, this is bad. So it makes this smaller, which is a good thing, and it doesn't make this smaller, so we don't have to worry about, balancing the change in this and the change in this. It doesn't change this, and it does reduce this one. So this is definitely a better threshold. The threshold that gave us this dot is definitely better than this.
In other words, the new threshold for deciding if a sample is obese or not is better than the first one. Now let's increase the threshold so that all but the two lightest samples are called obese. The new threshold gives us this confusion matrix. We then calculate the true positive rate and the false positive rate, and plot a point at 0.5, 1.
Okay, what about this? Actually, this is even better than this one. The threshold that gives us this dot is better than the threshold that gives us this dot. Because again, we didn't lower the sensitivity at all, but the false positivity rate got smaller.
The new point is even further to the left of the dotted green line, showing that the new threshold further decreases the proportion of samples that were incorrectly classified as obese. In other words, the new threshold is the best one so far. Now we increase the threshold again. Create a confusion matrix, calculate the true positive rate and the false positive rate, and plot the point.
Okay, now we can't say necessarily that this is better than this, because although the false positive rate did decrease, the other one, the sensitivity or true positive rate, also decreased. So that's not necessarily clearly better than this. So we can't really judge between these two, but we can judge between this one and this one. We can judge between this one and this one.
Now we increase the threshold again, create a confusion matrix, calculate the true positive rate and the false positive rate, and plot the point.
Now, we can compare this one and this one, and we said we can't compare this one and this one, but we can compare this one and this one, and this is better than this.
The threshold represented by the new point correctly classifies 75% of the obese samples and 100% of the samples that were not obese. In other words, this threshold resulted in no false positives. Now we increase the threshold again and plot the point. Now we increase the threshold again and plot the point.
So which threshold is better, the one that gives us this one or the one that gives us this one? Well, the one that gives us this one is better because they both have 0 false positive rate, but this one has a better true positive rate or a better sensitivity.
Lastly, we choose a threshold that classifies all of the samples as not obese.
So now we raise it so high that everything is going to be called not obese, or it's going to be called red.
And plot the point. The point at 0, 0 represents a threshold that results in 0 true positives and 0 false positives. If we want, we can connect the dots. And that gives us an ROC graph. The ROC graph summarizes all of the confusion matrices that each threshold produced. Without having to sort through the confusion matrices, I can tell that this threshold is better than this threshold. And depending on how many false positives I'm willing to accept, the optimal threshold is either this one or this one. Bam! Now that we know what an ROC...
So there's no reason to go down this, so we don't want to change the threshold so that we go from here to here or here and so on. So we either want to choose this one. We don't want to choose any of these. And between this one and this one, this is better, so we don't want to choose this one. And between this one and all these, we don't want to choose. We don't want these. We just want this one. So we only have two choices: this one, really, or this one. So if you don't want any false positives, then you would choose this one. But if you're willing to accept some false positives, then you could choose this one. So like he says, depending on how many false positives I'm willing to accept, we would choose either this one, or that's one way to phrase it.
The optimal threshold is either this one or this one. Bam! Now that we know what an ROC graph is, let's talk about the area under the curve, or AUC. The AUC is 0.9. Bam!
Okay, the AUC is 0.9. What does that mean? So let's say the curve went from here and went up to here, and it didn't come over here and up here. Let's say it went up to here and then over. So again, if it starts here, goes up to here, but then it doesn't move over to here. Suppose the curve went up to here and over to there. Then what's the area that describes? So the area under this curve would be 1. This length is 1, and this length is 1. So it would be 1 by 1, or the area would be 1. So this is going to have less area than that because it cuts off this part in here is not included. So that's the area under the curve.
The AUC makes it easy to compare one ROC curve to another. The AUC for the red ROC curve is greater than the AUC for the blue ROC curve, suggesting that the red curve is better. So if the red ROC curve represented logistic regression and the blue ROC curve represented a random forest, you would use the logistic regression.
Okay, now double bam. Okay, so in other words, we can take different models. Remember, how do we get the different dots? By changing the threshold, but that was all for the same model. That was all for logistic regression. So this was the curve that we get for logistic regression. Now we could use some other model, some other algorithm like J48 or naive Bayes or neural network or something else, and we could do the same kind of thing. Change the cutoffs maybe. We haven't talked about cutoffs in those algorithms, but it is possible to use cutoffs in them. So we could take, say, J48 and change the cutoff, and so you get every time you change the cutoff, you'll get a different dot, but it would be different than the logistic set of dots. You get a different set of dots, so that would give you a different set of dots for J48. So you get a different ROC curve, and then you could say, well, which one is generally better? And the one way to decide is to talk about the area under the curve. So if the red one has a greater area under its curve than the blue one does, so we would say that a model that was expressed by the red one is better on average, or on the whole, better than this one. But that doesn't always work, because you might get a point. It's really, you don't really, when you're running the model, you don't use lots of different thresholds usually. So you just choose a threshold, and so you don't have the whole curve, you just have one point. And it might turn out that one of the points here is not as good as one of the points here for whatever you're doing. Let's just say that you can compare models by looking at the area under their ROC curves, and that's called the AUC, area under the curve.
Double bam! Now, one last thing before we're all done. Although ROC graphs are drawn using true positive rates and false positive rates to summarize confusion matrices, there are other metrics that attempt to do the same thing.
So we may not use the same axes. So, for example, people often replace the false positive rate with precision. So precision is another measure that is in that Wikipedia page. So we could have that here.
For example, people often replace the false positive rate with precision. Precision is the true positives divided by the sum of the true positives and false positives. Precision is the proportion of positive results that were correctly classified. If there were lots of samples that were not obese...
So if your data had many samples that were not obese, then remember we talked about this a little bit when we talked about imbalanced classes. So that means when one of the classes occurs much more frequently than another. So that sometimes happens, and then if that's true, for example, a classic example of that is when you're predicting credit card fraud. So, if you have 1 million credit card transactions, maybe one of them will be fraudulent. Most of them won't be fraudulent. Most people don't use their credit card fraudulently. So if you look at credit card data and you're trying to classify things as fraudulent or not, almost all of the transactions will be not fraudulent. So you'll have a very strong case of class imbalance. So he's saying if you had many not obese mice, you might want to use a different curve instead of the ROC curve.
Relative to the number of obese samples, then precision might be more useful than the false positive rate. This is because precision does not include the number of true negatives in its calculation and is not affected by the imbalance. In practice, this sort of imbalance occurs when studying a rare disease. In this case, the study will contain many more people without the disease than with the disease. Bam! In summary, ROC curves make it easy to identify the best threshold for making a decision. This threshold is better than this one. And the AUC can help you decide which categorization method is better. The red method is better than the blue method. Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more, please subscribe. And if you want to support StatQuest, well, consider getting a t-shirt or a hoodie, or buying one or two of my original songs. The links for doing that are below. All right, until next time, quest on.